give you an overview on what membrane technologies are and how they've been they can be instrumental in water treatment in commercial buildings, institutions, hospitality sector, and so forth. Let me start it. So, membrane technologies have been in use for quite some time, for more over 30, 40 years. It's nothing but a semi-permeable material which has selective passage of particles or entities, whereby you are able to achieve a desired filtrate. So where have they been applied? In general water treatment and waste treatment. You see them in
मोबिलाइजेशन का
drinking
अप्रूवल
water,
होगा तब जाके क्रिएट होंगे बैचेस.
desalination, in disposal, in reuse. In drinking water, you would see them, the current scenario where virus and pathological infections are on the rise. Technologies like ultrafiltration have been installed in various drinking water applications, be it municipal or institutional, for safe drinking water. And the use in desalination have also been there for quite some time. It has been a very fine replacement to multi-effect or power-based or energy-based desalination techniques. Thanks to the reduced cost of membrane manufacturing, it has made it possible to make arid regions near the seas to have water for all use, potable and general use. Today's presentation, we will focus mostly on wastewater, which is actually concerning disposal and reuse. Of late, you would see that the water quality, the requirements have been really pushed high. So in wastewater treatment, traditional technologies, I would name a few, like we have um, uh, aeration processes, which is like activated sludge processes, which has its own limitation. Of course, they are robust. They have their own limitations in achieving the disposal quality. With the growing population, there is not much space. So olden days, when you would treat water, dump it into the water channel upstream, downstream, there is a water treatment plant which can treat it and get it back into the usable cycle. But nowadays, with the growing population across the disposal stretches, it's no longer possible to handle with just conventional water treatment technologies. So for this reason, the water disposal standards have been risen to the level in a way where retrieving this water back from natural water sources like rivers or ponds have been made possible. And second, it's also our responsibility to ensure that nature is made available for the following generations. So to ensure that the water quality or the natural resources are remained undisturbed, we are trying to clean the environment, I mean, the disposed water to the maximum level possible. A quick view into what has changed. If you would see, even from 2017, the disposal norms have been made more stricter, where you would have a double-digit turbidity, double-digit TSS disposal allowed. Nowadays, it's made to like 5 ppm or 2 NTO. These are all from very recent municipal projects. Again, why municipal projects? Because the municipal agencies are very um, keen in ensuring that the water bodies are not infected by wastewater being dumped into them. So nutrients like nitrogen, phosphorus have also been reduced. Earlier, there was some level, there was an allowed level of fecal coliform that can be dumped because the biological, I mean the entities in the water like fishes and the other could also bring them down. But again, it was made to below detection level because there is already enough food for the flora and fauna in water. So it is our duty to bring them much lesser. So all these have actually pushed membrane technologies to be employed in wastewater treatment. So, if you would look at conventional in general, in the past, raw sewage is first subject to screening. This procedure is not very limited to municipal or large scale applications. It's more or less the same thing that any you know what you would say commercial establishment or institutional establishment would do, be it an apartment complex, be it an office complex, or a small smart city. The treatment is it's exactly the same. It's just that the scale would vary. Traditionally, raw sewage is screened. Immediately settling substances like removal grit is removed by fast settling. Then there is a primary biological treatment, where there wherein primary settling and the biological treatment, which would be a suspended form or an attached form being done. It could be in activated conventional activated sludge processes. It used to be aeration, surface or diffuse sort of aeration, and prior to discharge, it is subject to a secondary settling, and it was discharged into the oceans. I would not necessarily say it's ocean. It is sometimes discharged into the rivers based on the municipal discharge norms, or it was disposed into other water bodies nearby, or it is like pushed into the ground. The sludge, usually, it is subjected to sludge treatment. So this is anyway there. So this is not going to, this has to be there. And the sludge biosolids are taken for either agricultural purposes or drying places where it is either reused or safely disposed. The odor that is generated is controlled, and the odor control or the atmospheric pollution is also checked there. So, and this used to be the usual scheme, but we were talking about the discharge standards in the ocean. So when the discharge limits have been risen to level I mean, or rather restricted to a level beyond what the conventional process could do, the only other option is to have a tertiary filtration. And what does tertiary filtration involve? It involves membrane-based techniques like ultrafiltration or MBR. In select cases, so it could also be that after an MBR system, it can be discharged into the sea. Modern thought is that they could, since they've come to this level of treatment, they could just do one step more, and they could do a reverse osmosis, get this filtrate, which is to a potable grade, and use it for, or rather reuse it, rather than dumping this waste into the sea. And the sludge is anyway being managed, so the waste generated is anyway being managed by the waste management system. So you're actually cutting short the water cycle, like getting a discharge, again waiting for rains, again waiting for normal water recharge of water resources. We are trying to suck out water that is being, you're trying to extract usable water from the waste that is anyway going to be discharged. So how are they being used? Why is like conventional technology? There are many conventional technologies that are applied in this process. In the tertiary filtration too, after the secondary treatment, you could use basic extended tertiary settling process, tertiary settling technology. You could use a multi-stage sand filter, a multimedia filter, then or a disc cloth type filter. They are all definitely proven technologies, but they have their own limitations, for which membrane technologies have been, considered. The advantages that the conventional technologies are used is that it is lower in cost and cheaper in replacement. They're robust. They process more water per unit size. They can be placed outdoors. They do not they do not require pre-treatment. Higher pressure and higher temperature limits are not, I mean, they're having very wide limits, so they're not limited by higher temperature and pressure. In many of the wastewater treatment plants, oil and grease is a very common problem. So when these two, when oil and grease is coming in, the conventional filters can be handled. It's a rugged tool, and it can be handled when you have off-spec water coming in. But is this sufficient? So why the membrane technologies were being considered is this. Um, what you see here in this graph is comparing two filters. One is a granular media filter, which is more like a sand-based filter. Another is an UF UF output. So we are comparing the output of these two units. We are trying to check the turbidity of the output. So you would see the membrane-based filtrate output is very consistent. It's a flat line, whereas the output from the traditional depth-based sand media, you see there are spikes coming up and down, up and down. And this is also a consequence of not just performance, it's also because there is a change in feed quality, there is change in output quality. If you would see the chart on the right hand side, you would see that the red line is the output turbidity of a filtrate of a ultrafiltration plant, and the blue line, the green line is the pressure at which it's running. The blue line is the inlet quality, which is actually an output of a sand filter upstream a UF system. So you see, if there is any change in this field quality, you would see that the output is also affected. Whereas whatever is the input, the output remains constant. So this is one thing that really drove the use of membrane-based technologies. So the ability to deliver consistent filtrate quality, irrespective of the feed quality changes due to season, it could be changed due to improper pre-treatment, any suspended solids change in upstream processes are handled by such membrane technology. So that's the reason they are there, and that's the reason they found their space in municipal drinking water, and similarly in wastewater when the disposal standards are very critical, when the operators can be penalized for output change fluctuations in the output quality. This comes in very handy. And not just this, there are more challenges in conventional filtration. So I was talking to you about change in the feed quality, change in filtrate quality based on the feed quality. So after a cleaning process, the filtrate also does not meet filtrate quality. This is a very standard problem that you would see in much of many pressurized or depth-based sand filters. Like I said, it's the filtrate is subjected to filtrate quality upsets due to fluctuations in feed quality. This is what we show on the last we saw on the last slide. There are there are depth-based filtrations which need coagulation aids, which is to ensure suspended removes. Like you need coagulation upstream the filters to ensure that there is better removal efficiency. So this is an additional cost on operation. On environmental aspects, if you are using coagulants, you need to handle the sludge that is being generated through this. It's also a headache, and there is huge cost involved in transporting the vessels, which are, you might see the conventional filters are really robust, and they need heavy equipment investments, and they also take a lot of footprint when they've been installed. On the flip side, the advantages that you would see with membranes is that the irrespective, like if you would see there is no change in the filtrate quality because of the feed quality, there's no expectation in change in the filtrate quality because of cleaning also. So after cleaning, it's supposed
That's
to be
there.
much better. There and some filters also do not, I mean, some filters do use coagulants, but again it's not like completely dependent coagulants or pre-filtrates. It is only in additional, it's like flexibility of the filters to achieve better removal of organics in the water, but it is not like they're completely dependent. And even there are optimized techniques where you can use coagulation at much lesser level compared to conventional filters. So in all these respects, the membrane filters definitely score much better. Well, we did have some advantages on conventional filters, right? So can we see how they can be mitigated by membrane filters? So low cost and cheaper replacement is the argument that conventional filters have. So it's not necessary that the conventional filters are only cheap. Membrane filters can also be made cheaper. The cost total, I mean, you need to look at the total cost of installation for the project. So when you have a very strong pre-treatment, when you can operate a higher flux, higher flux means higher flow rate through unit area of a membrane-based filter, you really reduce the number of units, and you are able to operate at you're able to handle more throughput through a lesser unit size of the product. So whereby your opex and capex for the unit gets significantly less, and given the requirement for the filtrate quality, the degree of treatment that one must give post treatment is already being managed by knocking off one stage of a conventional filter with a membrane based filter. So this is one aspect where the lower cost and replacements can be handled by membrane based filters. um, I mean, a low cost a filter is usually, a conventional filter is usually placed outdoors. um, it's enough for the, I mean, why you would membrane based systems need indoor housing is, the body is usually plastic. It's made out of UPVC, and it just needs to be protected from UV. As long as there's some UV protection given, it can still be used. So you really don't need extensive or elaborate building construction for these membrane technologies. In fact, some of these depth-based filtrations also need a shelter overhead to avoid algae growth. So it's something like this similar provided to membrane filters could also suffice. um, it's that there is this belief that the sand filters do not require pre-filters. Of course, the membrane treatments do require some pre-treatment, but like basket strainers are really not big um, investments. Rather than killing the membranes by allowing it to face really troublesome water, keeping a small strainer upstream can really handle the make the unit equipped and handle worst case scenario better. Higher pressure and temperature limits is always a talk. While membranes have been nowadays, the new age membranes have the capacity to handle pressures up to 4 to 6 bar. And why would you really need to go beyond this in conventional water treatment? If you're handling more pressure, it's going to become like more like industrial waste. In conventional, in municipal or commercial wastewater treatment or water treatment, you really don't need such high pressure. And on the temperature, the bodies of membranes are already equipped to handle 40 degrees centigrade. I'm pretty sure nobody really needs to process water more than the room temperature of 20 to 30 degrees. So it's very much fit. So the pressure and temperature limits are no longer a problem. On ability to handle ONG, I would say the membranes for them, in conventional filters, it's just that the ONG is it's painful. It's just that it is hindering the process of filtration, and it's not detrimental to the membranes. Proper chemical cleaning and proper removal from the surface, be it multimedia filters or membrane type filters, uh, it reduces the headache on hindrance on filtration. So it has not a problem. If it's a problem, it's a problem for all the types of filters. It's not specifically for membrane filters. And ideally, as a good engineering practice, it is wise to reduce the oil and grease levels upstream rather than letting it to be managed by filtration processes. So all put together, you would definitely see that the membrane filtrations have as a clear advantage of being employed. So you have better and consistent filtrate quality. Lower chemical consumption can be achieved by optimal options, because in the initial stages when membrane filters were brought in, the perception that they should be operated at lower flow rates per unit area was all there. So I think once the operators take advantage of the filters operational limits, lower consumption, lower capex can also be seen by the operators. So in total, this will affect to lower cost of effluent treatment management. Since the membrane-based technologies are all automated and all requirements for operation is guided, so the chances that it would fail can be reduced by human error. So automation can reduce human error, and this is also being guided by technology suppliers. And in many instances, membrane filters like UF or MBR are being used upstream reverse osmosis systems, which require a very consistent filtrate quality. So it has also improved the RO life and RO quality has also been, RO replacement rates have also been improved. So thereby the OPEX part has been substantially reduced. So another point is, compared to conventional systems, the filters, since they can also handle a reasonable flow rates through minimal filter through a unit area. The footprints required for such technology is also low. Another advantage is that you can, since it's a pressurized process, you could also go multi-level. So you can also deck them one on top, making it fit for operation in a very small footprint. So now there are many technologies available. You might need to know which type that one must use. Um, so the first type of membrane that is being used for filtration is an ultrafiltration membrane. And again, in this, there are so many types based on how they're operated. If it's submerged, wherein membranes are submerged in a tank, and through suction, there is filtration happening. And there is also pressurized, where their fibers in a or in a vessel is pushed, where wastewater is pushed and the filtrate is collected through certain ports. They're either classified as ultrafiltration, microfiltration, based on the type of membrane. They're hollow fiber, flat sheet, tubular, spiral wound, metal frame, and based on the material, it's PVDF, PES, PAN, CTA, and how many. In case of hollow fiber also, you would have one fiber having single fiber or multiple capillaries in just one fiber. Direction of filtration can be in, out, and out in. So to not confuse you so much, the current practice is that there are so many options available. I can already give you how many are really in practice. In case of operation, both pressurized and submerged are in place. When there is a very strong pre-treatment available, when the feed quality to the UF is very fine or pretty consistent, a pressurized system is used. When there is very high uncertainty in feed quality to the membrane system, a submerged system is used, because here there is tolerance to handle the solids to a very high level, to as high as 10 grams per liter, whereas in pressurized it's going to be around 50 to 100 ppm of TSs. I would come to discussion on how to select between ultra and micro. Micro filtration was in the early stages of membrane-based filtrations. Ultra filtration came into existence little later. It is actually a cousin brother, I would call it. I usually call them. It's just that the levels of cutoff is too close. That modern advancements in ultra filtration has actually surpassed microfiltration. This has absolutely become obsolete in wastewater treatment. Amongst the membrane configurations in general wastewater treatment or water treatment, hollow fiber are the most commonly used variety. Flat sheet, tubular, spiral wound, plate and frame, they're all still existing. They're all on special applications. So if there is a very special type of waste that's being handled, so then you would use this. So majority of filtration membranes are in the hollow fiber configuration, and some in flat sheet, because this is due to legacy. Some of the membrane manufacturers are doing flat sheets. They continue to do this, and it has its own set of advantages too. In case of membrane chemistry, the old ones were cellulose acetate, then polyacrylonitrile. um, they had their own disadvantages. They do exist, but not majority applications they are. PES and PVDF form a very large space. They have their own they have their own advantages and disadvantages, but they are existing in water and wastewater treatment. They can be operated in out and out in configurations, and they are also available. The fibers are also available in single capillary and multi capillary arrangements. Of modular arrangement, the recent trends is to go vertical, because the horizontal was a start, and with the advancements in the vertical technologies, the horizontal has completely gone. There are replacements available, but this is no use in current trends. So let me let now you have so many types, and how do you really check which type you want? So these are a few parameters one would have to look at to ensure that the selection is right. So I mean, you really can't say one is right, one is wrong. It's like comparing apples and oranges. So it's Every invention has its own purpose, so you really can't undermine invention. It's more like purpose driven. So here are few parameters one usually looks in selecting the membranes. So one is the membrane's porosity. I will come to what it means. Then tensile strength and elongation. So the membranes are subject to frequent filtration. During filtration and cleaning, they're subject to pressure, they're subject to hysteresis, so there should be some losses. So due to the elongation, they could experience, they could be vulnerable for damages. So what's their tensile strength and how long can they be elongated? So this all judges the fitness of the membrane for operation. So should I consider PES or PVDF or PAN? It's all considered based on this requirement. The fiber's diameter, the wall thickness, the pore diameter, membrane permeability. Permeability means how much of energy I put in to filter a unit volume through a unit area of the membrane. So it boils down to how much energy I spend in getting a unit filtrate from the membrane. Because if I have a very high membrane resistance, then I will not be spending in less energy. I'll be spending more energy to get the filtrate out. Hydrophilicity of a membrane and the charge on the membrane actually governs a little bit of permeability, because the more hydrophilic the membrane is, the more water loving it is, the impurities can be rejected by the membrane surface and the passage of water becomes easier. So the more hydrophilic it is, the better it is. How much is the surface roughness? This is to and it morphology. These are all like defines how the fouling tendency of the membrane would be. So the last thing is about the chemical tolerance. If the membrane, again, this also is talking about this, the material of the membrane. The better is the chemical tolerance, the better the many options that the user has or the operator has to clean the membranes. For instance, there is organic fouling, and in case of organic fouling, you need to reach a pH almost more than 12. The chemical resistance of the tolerance of the membrane has to be till this level to for you to enable this cleaning. And similarly, if you have to go to inorganic cleaning, you need to go to pH less than 2, and the membrane has to be tolerant. So this is something that's very critical to ensure that the selected membrane is fit for operation. So all these parameters are usually looked into, and for this reason, PES and PVDF are usually the most common option for filtration process, like membrane-based filtration processes. So let's know what sort of membranes are there. Like I told you, membrane filtration is a mechanical separation process, wherein selective passage or permeation of entities, like let's say the feed liquor, like you have water solution with all suspended solids, dissolved solids, whatever it is, like, or even colloids, bacteria, biology, microbes, everything that's there. And the membrane is when it's operated through a certain pressure or certain condition, it allows controlled passage. So in case of, if you look at this, you see four types of membranes are there based on the pore size. I was talking about nominal pore diameter in the previous slide. So microfiltration is having an effective diameter in the range of 1 micron. Yeah, so that's the reason it's called microfiltration. And ultrafiltration in the range of one in nanometers. It's that, and in case of nanofiltration, 10 times, and reverse osmosis 10 times more. So in microfiltration, typically it removes almost all colloids to suspended particles, but has the trouble in letting out some of the parts, like like the colloid. Sorry, it rejects bacteria and bacteria-like particles, but allows some colloids, suspended, of course, dissolved particles, and some viruses. So ultrafiltration is usually chosen for the reason that it only allows mostly the dissolved particles, which is can be handled by post-treatment technologies like UF by NF nanofiltration or reverse osmosis, which specifically remove only dissolved particles. And all, so after UF, technically all suspended particles are removed, and you're using the other membranes only for handling dissolved particles. So just for this reason, MF has been out of race of late. And I will also tell why MF was used in the past. Usually, it was like a combination of depth-based filtration and membrane-based filtration. You'd see filtration occurs by the membrane along with some level of cake layer filtration. So when you do a cleaning, the passage of uh, pollutants are much more easier in case of MF. In case of UF, irrespective of feed quality, so it's not dependent on the cake layer for filtration. So cake layer can make it much better than your filtered expected filter quality, but the minimum filtered quality is always assured in case of UF. And over a period of time, the once you're filtering, there are places in between the membranes which get clogged. The flux is a parameter which defines the filterability of the membranes. The more flux, that is more flow rate through a unit area of membrane, the better it is. Over a period of time, due to pore blockages, the MF declines much faster because the pores are open. It is more vulnerable to pore attacks, whereas UF is much lesser at vulnerable. So which means the lifetime of a UF is supposed to be much larger, much longer than an MF system. So besides this, there are many reasons that an MF-based filtration is used. Simply because the point that we were speaking about, consistency in the filtrate quality, for this and also ensuring all biology, including virus, of late, this is the most important thing that one must ensure is being removed. uh, for this reason, at least, that it is that UF is a better technology. Here's a case. I pulled out one case where you see it's for a resort, a commercial establishment, where the water is used for municipal irrigation, where the filtered water is used for irrigation of the, or what to say, the greens inside the resort complex, and also to a certain extent flushing requirements inside the complex. Besides this tech facts, let me throw light on what were the results. This was the reason that this technology was employed. Otherwise, it would have been conventional aeration, then tertiary clarification. It would have just been a tank. Maybe they would have dumped it, or they would have tried to use it for. I mean, it would have not been fit for even flushing. It would have been probably used for landscaping, but not since the disposal standard in these countries were really high, which is almost the same level that India is also coming up to. Membrane-based filtration was engaged in this place. So, what were the outcome that was desired and what was achieved is this consistent output, irrespective of the feed quality. I mean, you look at these parks or commercial establishments where the feed quality is definitely certain to change. They change because of the number of occupancy. Uh, it is also because of seasonal effects. So all put together has influence on the filtrate on the out throughput as well as the quality. So irrespective of these variations, the membrane works. Virus rejection was a key factor, so there was a requirement to ensure there is no virus in the filtrate. Remaining was like to ensure that the aquifers were recharged. It's being done. Waste load that is being treated, because it's been also reduced, because when you have pressurized membrane-based technology, the sludge, when you have very high recoveries, the sludge that is being developed is much thicker, and it dries off much faster than a conventional sludge. And by this agency is reusing some of the wastewater, so their dependency on the water grid is reduced. So their consumption, their purchased water source water is much reduced because of reuse of the existing system. Now we spoke about using just UF for filtrational technologies. You could do a little bit more by combining it with biology. And why do we do it? Because space matters. In conventional processes, you have biological treatment. Let's say you have aeration, submerged aeration, or surface aeration. Then you have a settling process and then tertiary filtration. So the purpose of MBR, we call it, is to reduce this space requirement and putting them together. So you're doing the settling and filtration in a membrane-based process, and this put together is called an MBR, membrane bioreactor. And you see here an SBR place plant of an identical capacity uses almost double the space that an equivalent MBR plant would take.
Our post-graduation
And
activity.
why has MBR found its place in such wastewater treatment? And this makes a lot of meaning in the commercial wastewater treatment, because of these three principal requirements. One is reuse. There is when there is a very strong need for reuse, when there is a requirement for checking the effluent quality, and there is when there is heavy pressure on reducing the footprint. In all these cases, I bet you the MBR is the best solution that a user can pick. And what would be the need for use? It could be for irrigation, it could be used for landscaping, it could be used for industrial reuse, like in boiler feeds or processed water. This could also be, in case of in apartment complexes for HVA, in office complex for HVAC water treatment. In case of apartment complexes or office complexes or townships, it could be for the greens, the golf courses, the parks inside the facility. Effluent quality has been tightened. The biological nutrient removal has been tightened. You need to really check the nitrogen and the phosphorus levels, and you definitely need a proper biology treatment attached with a membrane-based filter technology to ensure that you are achieving the defined filtrate quality. And last but not the least, you are also being pushed nowadays to consider the water treatment done in a very small space. So when there is a capacity expansion, when there is a limited space, when you want to go underground. So if you look at these office complexes, you would see that the wastewater treatment facilities are placed underground, and it's absolutely convenient for these MBR systems to stay there. And you're like trying to convert MLSs close to 5,000 to, I mean, 5 to 10, 5 to 15 grams per liter to a TSS of almost less than 1, which is phenomenal. And you ensure that the turbidity is less than zero point 0.2, which is perfectly fitting in the disposal standards with a BOD of less than 3 ppm. And why this is over conventional water, like this is also a study that was done as early as in 2012. What you see here are comparisons on capex and opex on conventional activated sludge process with an MBR system. In olden days, there was no pressure on the nitrogen limits or the phosphorus limits. So the conventional processes are okay. When there was a little bit requirement on seen on the nitrogen limits, the nitrogen treatment has to be improved. So you see there is marginal increase in the conventional processes. And when there is also nitrogen and phosphorus removal, you see it's really growing high. So because when you really have these two removal being there, you need more land space, you need special tanks to get rid of them. Then you have, when you add primary treatment to it, it gets even more. When there is warmer weather, when there is no enough space for biology, you need to bring down the temperature. So you need to have specific arrangements for that. It gets even more expensive. And number two, uh, set aside all this water parameters. Like I said, water quality and quantity, it's really hard to define because based on number of people using it, they're based on season, the quality keeps on changing. So there is a peak factor that is always needs to be considered. So if this has to be also roped in, with high different standards, MBR scores much better than conventional processes, be it in terms of capex or opex. Consolidated MBR plant is going to be very cost effective, and this ensures that the entire water economy or ecology inside the complex is going to be well balanced with such membrane-based technology. MBR has its application in many places. In commercials, like I said, it's going to be in green building. Green buildings do recommend reuse of wastewater, and this definitely fits in such membrane-based technologies. And smart cities, of course. In municipal, we also see a lot of large-scale, municipal organizations entering into membrane-based technologies, where you have conventional processes and you have the same footprint and you want to increase the throughput of the same plant, you just dump in membranes in the existing aeration facility and increase the capacity of the wastewater treatment facility. So this also seeing traction in the municipal plants. What are the advantages here in membrane based, I mean MBR sort of technologies, that you of course get the basic advantage on using membrane technology: consistent treated filtrate quality, high rejection of organics and solids, because this is something you need to ensure is not getting back into the natural water source. On the construction front, you have a very low footprint, so your cost of construction is going to be cheaper. There is no sand filters. It's a very modular plant, so it can be done in. I mean, the technology is now being in existence for more than 30, 40 years. So I mean, employing this is not a big deal. Like I showed you, the operation maintenance, since it's completely automated, handling this is not a big deal. And since it's a highly meticulated process, so there is not much sludge trouble that you would see in such membrane-based bioreactors. Since they're equipped to handle high flows, um, sudden flow changes are all manageable in such MBR-based systems. Now, there is always this question coming up. So when should I go for MBR and when should I consider traditional membrane-based filtration? Traditional membrane-based filtration, as in you already have a biological treatment like settling, aeration, secondary clarification. Is it fine if I just have a UF then post-treatment if required, or should I go in for an MBR system? In case there is an expansion plan for the same capacity. If it's only filtrate quality needs to be improved, then one would go for membrane filtration. Like you could just have a UF after the existing plan. If you're going for an enhancement of capacity, yes, MBR. Of course, that's what I was trying. If it says filtrate quality increase, you can just go for this. If both combined, obviously MBR becomes the best solution here. If you have footprint constraints, MBR is the best solution. If there is space available, and if you feel I can better, section the processes, I have better control on biology separately, I will do my filtration separately. Then they go for the filtration process. Like you can use a UF after conventional biological treatment. When there is long sludge retention times and you need to reduce that, then MBR again comes into picture. Generally, MBR works in the range for MLSs ranging from 5 to 15 grams per liter. And the SRT, again, this is depending on the wastewater, it can be from 5 to 40 days. The sludge production is only like 0.1 to 0.7 kg SS per kg BOD removed. So that's the level that it is. Um, the operating flux, like I said, the flow, the throughput per unit area of the membrane, it's around 15 to 45 units. And the pressure it works it is around 60 kilopascals, so 65 bar. So I mean, that's the maximum it would need. Sorry, 6.5 bar. That's the maximum it would need. So it's not a very challenging option. Um, of course, what is important? So what does a customer, what was a user look at? So conservation of space, consumption of chemicals, involvement of technology supplier, management of biosolids and its disposal, how much of cost of power, quality of the effluent, and how is it fit for reuse, using existing structure, and total capital expenditure. Usually it's only this that is being looked at. I'm telling you, see, once when all these factors are considered, because only when you look at capex, the other factors are overlooked, and costs employed in all these other factors actually play a very significant role. And if one tries to balance out all these parameters, and it would be easy to find out which technology to be picked. Like in filter membrane filters, even in MBR, there are many formats that is available. One is in the olden days, it used to be a flat sheet. It got upgraded to hollow fibers. Then came a hybrid system, which is actually a combination of flat sheet and hollow fiber. Um, Switching from polymeric materials, there are manufacturers who started making in ceramics. When we talk about commercial wastewater treatment, commercial as a, I mean in terms of wastewater treatment or water treatment in office complexes or buildings or in smart cities, um, the ones that is predominantly used are hollow fiber or in very rare cases flat sheet. The hybrid and ceramic are in making. Since hybrid is a combination of flat sheet and hollow fiber, it also has it has the advantage of both. It has the disadvantages of both. So it is more into large scale applications, very specialized applications that they are used. And ceramics are definitely very futuristic, but due to its high costs, they are not finding their space into regular waste treatment. So they're into very high specialty applications, or in businesses where the treatment quality or uh, the affordability to membrane-based technologies are high. Then these technologies are used. So we will stick to our discussions on these two types. Hollow fibers have been used much more than a flat sheet, simply because in a unit area you can actually offer much higher filter area. One reason, and second thing is flat sheets have the challenge of having point defects. So if you have a point on a sheet being damaged, you have to either live with the damaged sheet for a long time, or you have to get rid of one sheet, which means you have lesser filter area available. Whereas in case of similar challenges in filter fiber, if you have a broken fiber, you just knock that off and you can continue operation. So reducing one fiber does not really reduce the available filter area significantly. So practical reasons, hollow fibers are used in most cases. So again, in hollow fibers, there are two types. It's the fibers can be just single unit fiber, or it could be a fiber with a base fiber, and it's being covered with another material. It's like you have two layers of a fiber. We call that laminate, and if it's just going to be single material, it's called a monolith. In the monolith process, the fibers are drawn in such a way that there is a foam and it's an asymmetric structure, where in the production process itself, the outer layer is made filterable and the inner layer acts as a supporting foam. In case of laminate, an inner layer separately manufactured and outer layer is laminated over it. So what are the problems that you would generally see in these sort of systems is that the laminates are more vulnerable for damage. Like, they can peel off. Of course, they talk about higher strength. The braided support structure has higher strength, but when the filtering layer gets removed, the braid only remains as a support structure without having proper resistance for filtration, whereby the main purpose of your filtration, achieving the filtrate quality, is compromised. So this is a quick view on the two types of fibers. In a monolith, you just have one material. In the other, you have two materials. So which actually will have limitations of two materials in usage of chemicals. The tensile strength is low to medium, which is sufficient. Reason is you're not going to elongate and pressure, change. I mean, you're not going to manually mechanically elongate the membranes frequently. So it is sufficient. It is just sufficient. Having extra high tensile strength is good, but it's about what's the purpose. Um, a proper crystalline structure can ensure that there is proper resistance from the membrane surface. Higher chemical tolerance, chlorine tolerance, basically can ensure that the membrane can be cleaned at higher concentrations. So the higher concentration, like, in case of wastewater, when there is organic load, the, the the easiest thing that an operator would do is to purge the system with chlorine. And if the membranes fail for chlorine attacks, then the very purpose of using a membrane filtration would fail, and you will not get the defined filtrate quality if the membranes fail. So the most important quality that a membrane should have is a very good chlorine tolerance in case of an MBR. The higher chlorine tolerance is, the higher is the membrane life. then is there a possibility of delamination, as in is there a chance that you will peel off in case of a single material? No. And of course, if it's laminated, definitely can get delaminated. In and there is also a certain requirement for slacking. I will come to this in the next slide. When you keep a, this is how a membrane module, an MBR module looks like, and you see there is a small slack. There is this slack kept at the bottom so that when you're cleaning the membranes through air, this free space is there so that it just doesn't snap off from the uh, catching potting points. Like it's the fiber here is held at two ends of the membrane module, and this should not snap by doing any mechanical cleaning. So if the material is the same, the slack arrangement given shall remain the same. If there is two material available in the same fiber, due to the change in temperature or operating conditions, this arrangement has to be constantly being changed from time to time. So as you know, uh, due to temperature, they can get tightened, they can get loosened. So this slacking has to be adjusted from time to time, which is not a problem if it's going to be a single type membrane. When you see, this is a very close shot of a two-layered a membrane, wherein you have a braided structure and there is a membrane, like filter area that is laminated over it. When there is high pressure, when there is air-based cleaning already happening, this structure is likely to get peeled off. So if you have very strong fiber, doesn't really help. The high pressure or the mechanical conditions given are the fiber actually is able to handle, but the filter area is not able to handle. So this is something, this is food for thought. So when you're selecting the filter material, one must take care that there is no chance that the laminate is going to get removed. And what more you need to know when you're designing these plans, you need to know the capacities. There is an average flow, there is a peak flow at the time of start. There will be a certain flow that would only come in. So it should be fit enough for all these three. It's actually a biological filtration system. So if the biology sets up well, your membrane filtration will also be very fine. So while designing, one must take care of how the startup flows, average flows, and also the peak flows per day, per month, and per year is planned out. And also you need to know the influent quality by source, whether it's wastewater, is it like river water, like surface water, or is it going to be specialized industrial wastewater? How much is the solids loading rate? Other parameters like TSS, turbidity, ammonia, TK, and phosphates, BOD, temperature, and so forth. So once designing, one must take care of these parameters too. Typical elements of an MBR would be this. You have a membrane submerged in a tank. There is sludge, there is a feed coming in through, and recycled sludge taken out. There is air blower for cleaning purposes. There is a filtrate suction sucked by a pump, and the filtrate is collected. A cleaning arrangement is provided. So this is all what you would see in a typical MBR plant. A very important thing in terms of for an MBR operation or any membrane filtration, it's the pre-treatment. The better is the pre-treatment, the better is the life of your MBR. So you can take the system can handle eventualities, but continuously loading it would be it would be not a good idea. For example, if you're it's like running on a traveling on a rough road. If you have a smooth road, you have a very fine, you can have a very good drive. If you're always going to have rough roads, you're definitely going to harm your vehicle, and you should choose a much robust vehicle for that for that aspect. Once in a while, if you're seeing bumps, it's still manageable. So to handle this rough roads, you need to have a very strong pre-treatment. Proper removal of particles upstream is very critical for longer membrane life, reduced maintenance, because if you're going to get the membranes deal with high suspended solids, you'll have frequent cleanings. The overall efficiency of the membranes would come down, like you would take it for regular cleaning quite often. So it's definitely a cheap insurance. For a very successful MBR operation, this is very key for many operational complexes. The first thing is the headworks should be fine, like your pre-treatment for grit removal, or if it's all fine, then you have to set your biological treatment well. So if you're missing out, for which you should know the water quality, the influent type, and also the arrangements like aeration and all are in place. Then the membrane system has to be handled well. For the membrane system to be handled well, you have to know the proper selection of membranes, cleaning regimes, distribution of solids within the setup, aeration, how the aeration is also distributed well, and very minute thing is how well it's been installed. Are all the equipments that is required for monitoring being in place during the time of commissioning? Were the membranes being properly um, flushed, and are they properly cleaned prior to operation? If the calibration of instruments are all proper, then monitoring. So when membrane suppliers do provide guidance in control philosophy, operational philosophies, and the equipment requirements. So if it's all being incorporated as something that needs to be taken into control. Of course, this is all coming from experience and validation from the technology supplier, and I believe you will be able to find out some of the leading technology suppliers, and they can definitely help you achieve a very low cost ownership of membrane plants. There are many membrane plants available across the globe. These are a few from Dupont's Memcor series MBRs and submerged systems. These are mostly in for municipal applications, and municipal application means it can definitely fit into these commercial applications too. If it can fit into large applications, does also fit into the lower ones. Here's one case where it was reuse that was planned over, because the challenge was expansion. The filtered quality was made stricter, and so it was no more viable to use conventional activated sludge process. So we are talking about reduction of BODs to less than 1, ammonias to less than 0.5, and nitrates to less than 10, which is not actually required. So it was also a consequence. TSS and turbidity far better than the limits that is really required there. Similar case in Australia, where this is again the largest MBR plant in the country. Um, I mean, the outlet parameters are not disclosed because it's a municipal plant, but what we certainly know is the requirements that they have specified have been achieved. So I can certainly say that BOD less than 6, around 5, and ammonia TSS less than, it's actually much less than 5, it's around 1, and NTU turbidity is also less than 0.1, and this almost nil, fecal coliform is almost nil. So this takes me to the end of this presentation. So if you have questions, please feel free.
Yeah, Mr. Amrit, it was a very nice presentation and full of knowledge.
Thank you,
So,
sir.
yeah, now it is a time for question and answers. If somebody has a question, so he can raise, and he can put a question in the chat box. So we will take that.
Yeah, good morning.
Good morning, sir.
Sir, you are telling that this quality of this discharge water treatment, this NOM 2019 norms,
Yeah.
you are mentioning it earlier. You are for this coliform level, you have mentioned BSD. Can you
BD.
elaborate a little bit about that
No,
BSD?
BDL, I said below detection levels.
Yes.
Yeah, this is still around 1000 MPN per ml. That's still the requirement in some cases.
Okay.
This is a recommendation in few municipal projects in India. So this has been a requirement that's been specified. So that I'm trying to highlight, this is more
Okay.
like a requirement being asked.
Okay.
It's not, that's what I was trying to say. It is only the projects that are asking for it based on their requirement, and it's not a NGT norm. It's a recommendation, but not a norm.
But this facial coliform detecting to BDL level is nearly, it is very difficult. No? It's in what in my
Sir,
experience.
with membrane technologies, it's possible, sir, because you're actually knocking off all the biology through this process. So, and it's a very common practice in Middle Eastern countries, like if you would say Qatar. You would see that the filtrate quality defines virus rejection to almost log 2, 99.99%, and that has to be
Okay.
guaranteed. So in such a case, it would be log 4 reduction of bacteria. I think these
Okay.
coliform all fall under this category, and they can get rejected that level. Technically nil. That's what they want, and it's possible. Yeah.
I think India, it is technically nil achieving target. Is it possible? On this last question, Mike.
Sir, it's possible. Whether we need it on large scale is the question that we have. And today's discussion, I'm positioning it mostly for commercial applications.
Yes.
I also do live in an apartment complex where I
Yeah.
would want to have my tap water free from all this. Like even if I have flush water, I
Yeah.
want to have it free from all this. Here
Okay.
too, we have an SBR technology followed by UF
Okay.
treatment. So yeah,
Okay.
that's the requirement. It's like more like for apartment complexes, they have this in place.
Thank you, Mr. Giridhar.
Yes,
Thank you
sir.
very much.
Thank you, Mr. Shridhar. Any other question, please? If somebody has a question, they can put in the chat box or they can ask. So, Mr. Shridhar, sorry, Girdhar, it is now my request that kindly share your email address on the
Certainly,
chat
sir.
box. Yeah, and if you can also share a contact where, because there are people who are looking at different modes on the like Picky Bike and YouTube and other places. So if
Hmm.
we have question, so we can put directly those questions to you. And so can you put it, sir?
Yes, I'm just searching for the chat box.
Okay.
Yeah, just a second.
No problem. No problem.
Yeah. So just a second.
Or what
So,
I can do is I will
so
take it.
yeah, I mean, this is my email address.
Yeah,
I hope you're able to see this. It's amrit.giridhar@dupont.com.
no problem.
Yeah, so if you
I
have
have.
questions,
Yeah,
feel to write to us.
yeah, yeah.
And I'm also available on LinkedIn and online platforms, so we can also post questions there if need be.
Thank you, Mr. Amrit. It was a very knowledgeable and elaborated presentation. Really, it was very nice. And would you like to give a closing remark on this? Then we will close. Like you would like to tell the industry something about the particular your product that this is like any closing remarks to the industry.
Yes, I mean, I had this question on is it possible to have such technologies in India? There's always the question that has cropped up. So when I started to um, this question on can India afford membrane-based technologies, and I should tell India has been front runner in to some of the European municipal agencies demonstrating that we can have such membrane technologies for our daily needs, like for daily potable water uses. Example, I would call Chennai has a very strong example. Be it desal, we have the first municipal desalination project in Chennai. We also have two wastewater recycle facilities in Chennai, and there is also a wastewater-based recycle facility in Surat. These are all front-running technology, front-running examples to many of the agencies, municipal agencies in India and abroad too. So they're looking at how these are functioning and to fine-tune them abroad. And I did not talk about one specific point, which is more to on municipal aspect, that's micronutrient, micropollutants, which is taking a toll on water bodies. And now there are many technologies being worked out in combination with membrane technologies to achieve this, fine water bodies across the globe. So this is definitely a way forward. I'm pretty sure we are not the only people alone promoting such technology. There are many, and I would advise the buyers to take a keen look at how to select the technology. I've given sufficient guides to select the right technology for their use. For any other support, we are always there.
Thank you, Mr. Amrit. And with these remarks, we will close the session. And in case we get any kind of questions, Amrit sir, we will get in touch with you.
Anytime, sir.
Thank you, sir. And thank you all participants from India. And we are really thankful to you.